Hello. In this video, we're going to talk about one specific type of probability distribution. One of the examples that we went through often is this coin tossing example. And this is a simple example of what we call a binomial random variable. And many experiments will actually result in data similar to this heads or tails outcome of the coin toss. And we call these experiments binomial experiments. And they're pretty rigorously defined. A binomial experiment is anything with one of these five characteristics: that the experiment consists of n identical trials, right? There must be n trials. Each trial results in one of two outcomes. We call one outcome a success. And again, that success is more based in our desired outcome. The other is a failure. The probability of a success on each trial is equal to P and remains constant from trial to trial, right? So between trials, there can't be any change in the probability, just like coin flipping, right? Flipping a heads or tails on the first coin flip and the 1,000th coin flip does not change. The probability of a failure, we are going to call Q, but it's just 1 minus P, right? The trials themselves are what we are going to call independent, right? The outcome of one trial is not going to affect the outcome of the other. So just because we flip a heads on the 7th toss does not mean we're going to flip a heads or tails, or we're any more likely on the 8th toss. And what we are interested in is the number of successes observed in the n trials, right? So let's look at kind of an example that follows this binomial experiment method. So let's say we have a geneticist that sampled 10 people and counts the number of these people who have a gene linked to Alzheimer's disease. And they want to find the probability that any one randomly selected adult in this gene has this gene is 0.15. Is this a binomial experiment? Does this satisfy those five conditions? So does it satisfy one? Yes. We know that there are 10 trials, right? We're looking at 10 people. Two, I can label a success of having the gene, and a failure is not having a gene. Again, this example tries to reinforce the fact that success does not mean a good thing, right? Success is a desired outcome. A geneticist may want to know how many people have a gene linked to Alzheimer's. Having Alzheimer's is not necessarily a successful thing, but in terms of a researcher, it's a desired outcome for them to continue their research. So in this case, we consider that a success. So we can distinguish these outcomes. 3, the probability of success, we're told, they find the probability that any randomly selected adult has this gene is 0.15, and that makes Q 0.85. So yes, these things are consistent. 4, the trials are in fact independent, right? One randomly selected adult having this gene does not affect whether the next randomly selected adult has the gene that is linked to Alzheimer's. And 5, we can in fact say X is the number of people having this gene. We can in fact count. So this, yes, this is going to be a binomial experiment. And the question then becomes, for each outcome X, what is its corresponding probability? How can we compute that in an efficient way? Do we have to list all of the possible ways? We did that in the last example when we had 3 coin flips. We saw there were 8 outcomes. What about if we have these 10 trials? Can we list all of these possible ways? The answer is we can. It's going to take way too much time. So we must need a shortcut to help us our way. In fact, we do get a shortcut. We get what we call the binomial probability distribution. And this gives us a way to find the probability of getting exactly K successes in N trials. So a binomial experiment consisting of N trials with the probability of success on any given trial being P. the probability of exactly k out of those n trials being successful, we're going to call P of x equals k, or we can just call it P of k, is going to be n choose k, P to the k, q to the n minus k, or just write it like this: n choose k all over k factorial, n minus k factorial. Again, this is n choose k, P to the k, q to the n minus k. Right? And don't worry, we'll do an example of this. However, because this is a specific binomial distribution, it has a mean, a variance, and a standard deviation. We're not going to have to use those sum formulas. And as we'll find out, if we know the type of random variable, right? If I know that this is a binomial probability distribution and a binomial random variable, we get shortcuts to find the parameters. For example, the mean, or the expected value of a binomial random variable, is just n times p. The variance is just npq, which makes the standard deviation the square root of npq. So let's just practice this. So for example, 5.6, we want to find p of equals to 2 for binomial random variable with n equals 10 and p equals 0.1, right? Again, all this is asking to find is p of 2. And so looking at our example all the way up here, it's going to be 10 choose 2, right? 10 is my number. In this case, 2 is going to be k. P, I know, is 0.1. So it's 0.1 to the k, in this case 2. Q, right? If p is 0.1, that makes q 0.9. So 0.9 to the 8th. Or 10 factorial, 2 factorial, 8 factorial, times 0.1 squared, 0.9 to the 8th. And I can compute this in our calculator and get 0.1937, rounding this to 4 decimal places. And it is customary when we're dealing with these types of probabilities to round them to 4 decimal places. All right, let's do a slightly more involved example. Let's say a marksman hits their target 80% of the time, and they fire 5 shots on the target. What is the probability they hit 2 targets? In this case, we're told P is 0.80 and N is equal to 5. I want to know the probability that they hit 2 targets. So again, that's just P of 2. And using the formula, that's going to be 5 choose 2, 0.8 to the 2, 0.2 to the 3. Again, if P is equal to 0.8, Q then must be equal to 0.2, which is how we get this value. 5 choose 2 is going to be 5 factorial over 2 factorial, 3 factorial, 0.8 squared, 0.2 cubed. If I compute that and round to 4 decimal places, I get 0.0512. All right, what is the probability that this marksman hits at least 2 targets? And this is going to be slightly different, right? We need to look at this for kind of what it means. So at least 2 targets, that means I want P of 2. I also want P of 3 and P of 4 and P of 5. That's a lot of situations to deal with, right? The probability of at least 2 targets. What might be easier is looking at the complement in a case where we see the word at least, right? There is also a possibility that this person hits no targets or 1 target. And so what we can do is think about this problem being the probability that we get at least 2 targets to be 1 minus the probability that we get less than 2 targets. And again, that's going to be 1 minus P of 0 plus P of 1. So that's what we're going to compute. We're going to compute P of 0 and P of 1. P of 0 then is going to be 5 choose 0, 0.8 to the 0th, 0.2 to the 5th. And P of 1 is going to be 5 choose 1, 0.8 to the 1st, 0.2 to the 4th. And if we compute this, we're going to get 0.00032. at 0.0064, meaning our probability that X, we get at least 2 targets, is 1 minus their sum. And if I compute that, I'm going to get 0.9933. All right. Let's look at an example of computing these parameters. In a recent survey, it was found that 64% of adults need vision correction for their eyesight. And if 652 or 625 adults are randomly selected, what is the expected number of these adults that need corrective vision? And what is the variance in standard deviation? So let's look at one. We're told in this that N, the number of people in our sample, is 625, and the probability that any one of them need corrective vision is 0.64. So the expected number, E of X, right, that's also, again, the mean. Because we know this is a binomial distribution problem, I can use the shortcut of NP. In this case, that's 625 times 0.64. And if I do that, we're going to get 400, right? That is the expected number of people that need vision correction. If I look at part 2, I want to know the variance and standard deviation. Again, the only value I don't have is Q, but again, remember, Q is just 1 minus P, so that's 0.36. My variance is just NPQ, so it's 625 times 0.64 times 0.36. If I compute that, I'm going to get 144. That is the variance in the number of people. And again, the standard deviation, the easiest calculation we ever do, it's just the positive square root of my variance. That's the positive square root of NPQ, which is 144, or we get 12. All right. Hopefully this was helpful. If you have any questions, send me an email. I'll be happy to Zoom and do office hours. If not, I'll talk to you next time.